Hey everyone, I'm another one of the members of the SUSCORD project here at Manchester University. I work with Peter, just got a lot louder, there we go. I work with Stuart and Peter. Now, a bit into what my project's all about is, much like the very good presentation earlier today, I'm also taking a combined experimental and finite element modeling approach. My focus, however, is going to be an electrochemical response model for a defective coating. We're particularly interested in its AC behavior, things like its impedance. How does this impedance response change as we change various things about the coating itself? Size of the defect, thickness of the coating, that sort of thing. Now, the system that I'm modeling, I've tried to show in a graphical representation here. This is not the exact geometry that is being solved for. This is just for illustration's sake. But in essence, there are two main components to the model: the coating and the metal. And from an electrical point of view, I'm treating them as parallel working electrodes. Now, the system contains 4 resistive elements and 2 capacitive elements present in these 2 pathways. I'll get more into that now. Now, this is an example of the global equivalent circuit, everything that's going on. But the main point of interest is, where is the current going to travel? The defect pathway or the coating pathway? The preference between these 2 electrical pathways is a significant factor in the global impedance response. So we'll go into the coating pathway at first. Now, with all of these pathways, it will have to traverse the solution resistance, so that will be there each time. But in essence, the coating is a parallel RC circuit. The resistance of the coating in this case being so overwhelmingly large that we often don't really consider it. It's often giga, tera ohms, so it's very often not active. The capacitance, however, is the primary method of current transfer across the coating itself. The second pathway is the defect surface. Now, the previously mentioned solution resistance, much like the pore resistance in this case, is being solved for as an ohmic star resistance. Now, the capacitive current density is solved using the equation shown below. The model operates in the frequency domain, which is why the equation may look a tad strange. Now, the more computationally expensive part of the model is solving for the Faradaic current density, specifically the corrosion processes on the surface of the metal. I'm accounting for 3 cathodic reactions and 1 anodic reaction. The anodic being straightforward ion dissolution into solution, and with the cathodic reactions present being the oxygen reduction reaction, hydrogen evolution, and water splitting. Now, the main one of focus here is the oxygen reduction reaction. The oxygen reduction reaction has a very significant mass transport component, which is key in replicating its behavior. Now, the equation shown below is a very, very long-winded way of pretty much just solving for the current over potential relationship going on in the situation. Now, I'm about to go through an example of a data set generated by the model across a very, very wide range of defect sizes. Now, the defect in this case is 1 nanometer, functionally an intact coating. In the Nyquist plot here, we see a vertical line, in essence, a pure capacitor. Virtually no current is traversing the defect because it is just simply too small. We also see this shown in the Bode modulus, with this diagonal line representing a pure capacitor and the phase shift being almost entirely at 90 degrees. If we make the defect 10 times larger, the Nyquist plot largely remains unchanged due to the defect still being so tiny. But if we look here, we can see the early signs of a resistive process emerging at low frequencies. Make it another 10 times larger. Now we're beginning to see things happen. This arcing of the Nyquist plot over is showing the emergence of the resistive process, specifically the Faradaic reactions. and the phase shift is moving quite rapidly towards 0 at low frequencies. Another 10 times larger, we're now seeing very prevalent bare metal behavior. Continue on. And at this point, we pretty much have a very large hole in the coating where this acts almost entirely as a bare metal electrode would. Now, as for the sort of thing I believe this model could be used for, detecting coating failure using impedance is quite straightforward, as I've tried to illustrate in the previous slides. Vertical line, good. Anything resembling a semicircle, quite bad. But this model aims for the damage to the coating to not only be detectable, but directly quantifiable. By allowing the model to be adapted to a coating system in use, we can see quite a lot of interesting points about the coating failure. At what point does coating failure become measurable? And ideally, we'd be able to collect a data set showing, for a particular value of impedance, more or less what size defect are we expecting here. And I've done a diagram here. The majority of the arcing I was mentioning previously happens between 100 nanometers and 10 micrometers in this situation. Is this going to work? Oh, there we go. As you can see here, the Nyquist plot arcs over quite rapidly, and then the impedance very, very rapidly goes quite a bit lower. This representing the emergence of the defect, which is a hell of a lot more of a preferential pathway. Now, for future work, the focus will be on using EIS, localized EIS, and the scanning vibrating electrode technique, SVET, to validate different aspects of the model. EIS will be measuring the global impedance response, and considering this is what the model is generating, it'll be quite important moving forward. Now, one flaw of EIS is that it purely measures a global response, which is very often sufficient. But if I want to begin troubleshooting my model and the data doesn't align up, what am I supposed to do? Where's it going wrong? That's where LEIS comes in. LEIS allows us to not only take impedance measurements, but to specifically take it at points within the model. You're able to use single frequencies to create a map of the impedance. So using that, I'll not only be able to see where the model deviates from reality, but the exact point at which this deviation is occurring. SVET is another method in the same vein as LEIS, but this works through measuring the current density across a sample surface. This will be quite key in verifying the DC behavior of the defect. What sort of potential and current distributions would we see when a current is applied, that sort of thing. Now, as for the validation process, I'll be comparing experiments which I'll be doing myself to a modeled system. Now, the idea would be I would take a coated sample and create an artificial defect. Using optical microscopy, I will get the exact diameter of this defect. I will then adjust the model to reflect my sample and then see where do things line up and where don't they line up. Now, to summarize, the finite element method has been applied to model the electrochemistry of a defect in an organic coating. One of the key focuses of the model is the preference between the coating and the defect pathway, and how this preference evolves as the system evolves. And finally, that the model has shown that electrochemical impedance spectroscopy can be emulated quite effectively, qualitatively lining up with about what we would expect. But the key focus now is quantitatively validating this, because at this stage, we're essentially looking at a well-educated random number generator. I'd like to make sure that it is aligning with reality. Thank you.
Thank you very much, Callum. Okay, we're open for questions.
When you talked about trying to verify your model with new experiments where you're creating a defect and it goes into acid, and I can imagine you've got like a coated carbon steel. So if you're trying to create a defect in the range between some amount of nanometers or millimeter,
Nanometers we're not even considering.
I was going to ask what sizes can you consider? Like, is it difficult to create a very small defect in maybe the micron scale? Because I would imagine that would be quite hard.
Getting into the micron scale will be quite difficult. We can move down to about 1 millimeter quite comfortably using mechanical methods, but anything smaller than that will either require a less controlled method or something a bit more specialized. One of the options we've looked into is potentially lasers, but we'll get to that soon. But yes, going below 1 millimeter is quite difficult. And even if we were able to make, say, a 1 nanometer defect, there would be no hope measuring anything from that.
So how thick is it going to be on your coating?
Say that again, sorry?
How thick?
For this data set just generated, it is 100 microns, but that can be freely changed.
Yeah, I found that when it exceeds 300 microns, the impedance is not quite well on this thickness. Even we can't distinguish corroded sample and not corroded sample. Are you going to change the thickness on your validation?
It could be something to look into, but it is not the focus moving forward.
Further questions?
How have you evaluated the RP resistance of the pore?
The pore is being solved for using the value for the solution resistance. It's pretty much treating the pore as just a solution-filled cylinder, and it is taking the value for the solution resistance and just solving it from within that pore.
And how did you consider the chemical effects of your anodic and cathodic processes that occur with the porosity?
If you're talking about as in the effects that the products would have on the metal.
Certainly that should change the conductivity and mass transport within the electrolyte in the pore.
The change in conductivity, I believe, is being reflected, but I'm not quite sure about. Could you repeat that second part again, please? Could you repeat that second part again, please?
It should change the conductivity
Mhm.
of the electrolyte in the pore. That's the main thing.
Yeah.
And concentration of species as well.
Yeah, the change in concentrations is being accounted for.
Transport limitations.
Yeah, the mass transport is being accounted for as well, with a specific focus on the oxygen reduction reaction. Because the scope of this model is largely focused on alkaline conditions, we're also looking into the mass transport limitation of the hydrogen reduction reaction.
Perfect. And you should line him up as the first year examiner or second year examiner. Okay, 5 years. Okay, good. Okay, perfect. I would say,
Thank you.